Hi, this is Robert Bolaños. Welcome to a episode on how to design an input filter and check for the stability using Bache's Victorian negative resistant model. In this presentation, I'm going to show a design procedure to meet the conducted emissions. Specifically, since I do space, typically we use the MIL standard 461C. I'm going to define the Middlebrook Criteria and then show how to calculate the converter's input impedance, show how the damping of the input filter, how it affects the output impedance of the input filter, and then I'm going to show how you can use a negative resistance to actually model the converter's input impedance and show how to simulate that. And then lastly, I'm going to show a comparison between the negative resistance model and a switching model, and you'll see that they're pretty close, or they're almost a match. Some of the relevant videos that I've done are listed here. Input filter design, which is part 9. This video is mostly based on that one, and since I have 2 other videos, part 9 and then the inrush, they're all separated, so I decided to make this video to kind of put all 3 of them in a way together. Although the slow start circuit is not not discussed in this video. Another videos that you might be interested is by Professor Sam Ben Yakov. Here are 3 of his videos that he has produced. He goes into great detail. I highly recommend that you take a look at those as well. Now, when you're designing an input filter, it's an understatement to say that it's a very important part of the power supply. If you neglect it, you can design a good switching power supply, but then if your input filter is not damped or properly designed, you can have a converter that will be unstable in certain conditions. So the purpose of this video is to show at least a design procedure that I've used, and also how to simulate or use the negative resistance model that I first saw in on one of Vache Viporian's book. Okay, so here is a very simplified input filter, and we're going to start on this section. This is the bus model. I'll call it the V bus. You have your input voltage, and typically the bus will have a certain impedance as well. So this is your input voltage coming in, and typically you will have a bunch of other devices. You might have a LNA, a low noise amplifier, and other connected at this node. I'm going to call that the V-bus node. And then you'll have a differential inductor, and that the purpose of the inductor is to present a high impedance. Well, high impedance to what? It's going to present a high impedance to this current. Okay, so here I'm using a current source, and I'm using this to model your converter. And you can define the rise time, the on time and the off time, and so forth, and you can mimic these waveforms. Now the waveform that I'm going to be using will be that of a flyback, and this would be DCM, discontinuous conduction mode, and this would be a forward. Looks something similar to that. And this, of course, would be a CCM, continuous conduction mode. But for this example, I'm using a flyback. So you can use a current source and you can mimic the converter without having to use a huge switching model. Just a simple SPICE element is sufficient to give you some very good information. Okay, so this current, which should look something like this, and I believe in the example I'm using 5 amps. That 5 amps, what you want to do is you want to be sure that your capacitor actually shunts most of the current through this capacitor. And this capacitor, typically you want a low ESR cap. So the ESR, you want it extremely low. And so the capacitor will present a low impedance, so you can shunt most of the current through here. And then the inductor presents a high impedance. That way, when the current is coming this way, well, it looks at this path, and the current will choose the lower path, which hopefully will be through the capacitor, while the inductor shows a high impedance path. Now the main idea is you want to keep the current and the V bus, you want to minimize it. Okay, in this slide you can see the current a little bit more explicitly. So basically your current is going to go up here, generated by this current source. And remember, this is the model for the converter. And you want basically the current to be shunted mostly through this, and there will be some through here. And you want to minimize the V-bus current, or at least the current going into the bus. You want make sure that that's clean. You don't want it. You want to basically minimize that as much as possible. Now, one of the important parameters that is tested on most power supplies, especially in space rated, is conducted emissions. Conducted emissions, again, it's basically how much current is allowed into the bus. And I've used the MIL standard 461 C standard, and the units that it's specified as dB microamps. So this is the plot. This is for the CE03 narrowband emission, and this is the diagram that you would use to start your design. So here you have your x-axis, which is the frequency, and then you have your y-axis, and this is the dB microamps that is allowed back into your V-bus. So the first thing that you do is this is the chart that you use, and in the example that I will use is a switching frequency of 100 kilohertz, and 100 kilohertz, this would be 1 megahertz, so this is 10 kilohertz. And if you go up and then to the side, you can see according to this graph or plot that you're allowed 60 dB microamps, which is right there. So now what we have to do is, since it's a dB microamps, you want to convert it into a absolute, and you use this equation. This is what you get from the graph, and you end up with this equation. So the current conducted emission bus, and I can call it more like a limit. This is the limit max. You can think of it that way. You're only allowed basically 1 milliamp of current into the bus at 100 kilohertz. Okay, so once you have that, the second step is you want to calculate or simulate the primary current. You can do that either by using the switching model in SPICE, or you can use a current source to mimic your converter. So this is a simulation from the switching model. And basically you want to make sure that you get the time rise, the fall time, and the period, and those parameters you can go ahead and put them right here, which is rise time, fall time, and then the period, and then the width you make it really small, and then you make sure that you put the peak current. In this case is 2.4, so this is the peak current. Once you have that, then you have a pretty good model representation of your converter. In this case I'm using a flat pipe converter. Once you have that, you want to do a FTT of your waveform. You want to look at the spectral, and specifically what you're doing or want to know is at 100 kilohertz you want to know what the fundamental current is. In this case, this sawtooth waveform, its fundamental is basically 465 milliamps of current. That would be the fundamental. Now remember, this is what's in the primary of your converter, and you want to limit no less than 1 milliamp into the bus. Okay. So basically this is the current that we got from the FT, and this current is at 100 kilohertz, and you want to limit that, or at least most of it you want it shunt through this capacitor, therefore limiting this to 1 milliamp. So that's the goal of your input filter. Okay, so now you calculate the maximum current allowed into the bus, which we already did the math. So here we know that the bus, the maximum is 1 milliamp. Okay, so now that is entered right there. I call it the current conducted emission bus. And then we know what the primary FTT, we got this from the FTT. So we have these two parameters. So now we want to find out what kind of attenuation do we need to achieve this goal. So basically, you use this formula, which is attenuation, which is 20 log the ICE bus. Remember, this is supposed to be 1 milliamp. And the primary current is 645 milliamp. So to get that attenuation, you need negative 56.2 dB. Okay, so what that means? It means that you want the input filter response to have basically a second order response, and the second order because it's a LC, and at 1 kilohertz you want to make sure that you have a attenuation from 0 dB. You want at 100 kilohertz to be attenuated to 56.2. So this is basically what you want. If you look at this curve, you can see that it's steep. That's a negative 40 dB per decade. And then you can see here there's a 0 here, and this should be negative 20 dB per decade. Okay. So now that we have that attenuation and we know the switching frequency, in this case we're switching at 100 kilohertz. With this equation, which basically the transfer function of this, you can calculate what is the resonant frequency that you need to achieve the input filter response. So in this case, I just picked 43. I picked this value, and then I can calculate what inductor I would need to achieve my attenuation. Okay, so now I have basically my capacitor, which I select, and then this inductor that will resonate at actually it should resonate at, hang on, this should be 3834 hertz, I believe. Okay, actually I think it's 3934 hertz. So that's the frequency. So this is 3934 hertz. So let me write it here, 3934 hertz. Okay, so once you have that, then what you want to do is you want to calculate what is the characteristic impedance. And this is very important because whatever your impedance is, the characteristic impedance, and that's the square root of the inductor and the cap, then you will use that impedance to damp your output filter. So in this case, Z damp, you will use a resistor in series with a cap. And typically the C damp, that's usually what I call it. You can anywhere from 2 to 10 times whatever your regular cap. And in this case, if I have a let's say I'm going to use a 10 times 43 microfarad, then I will use a 430 microfarad in series, basically in series with the C damp with a R damp, and this should damp your input filter very well. Okay, so here are the values of a 46 and then a 38. I believe that's what yes, 46, 38. And then here is the value 945. So I have that value here. In this cap, like I said, it can be anywhere from 2 to 10 times. It looks like I use about 4 times. Okay, 4 times there. Okay, so now I can do a transient, and remember, this waveform is the waveform that we made that looks something like this, and I had a peak of 2.4. And what we're going to do is we're going to measure the current going through this current, which is supposed to be the primary, and then we measure the current that goes through that voltage source. We're going to measure this, and that will be your bus. And then you will take a FTT and see the fundamental and see if it meets the 431. Okay, so here is the results of the simulation. This is the primary current. Well, you can see it right there, 465. And then you can see this is just at about 1 milliamp of current, and this is what's going into the bus. So this meets our conducted admission specification. In this case, it's right on the edge, so you can actually make the capacitor a little bit bigger and shunt and give you a little bit of margin. Okay, so another thing that you want to do is, once you know that you meet the CE limit, then you do keep in mind that the simulation that you did, we did a transient simulation, and this is to see if you meet the CE, and you did the FTT. Okay, so now to check the output impedance of the input filter, you want to do a AC analysis, and what you do is you set the magnitude of the AC source to 1. So if you put 1 amp here and you have, let's say, 1 ohm, you should have 1 volt, which means that it's 1 ohm. Okay, so it's a 1-to-1 ratio if you make this 1 amp. Okay, so we run a simulation and we see the results shows that the output impedance is approximately 1 ohm. So if you take a look at this, typically this would look like a short at DC or low vary frequency, but this is a high impedance. This is a high impedance as well. No, actually a low impedance. And since this capacitor is much bigger than this one, or at least 4 times to 10 times, it is the dominant impedance. So basically this should be kind of like a short by FC. So if as C goes up, the excess C goes down. And basically you can think of this as a short. And if you notice, the R damp then dominates because it's bigger than this impedance, than the capacitor. So since this is 0.9945, basically matches what your output impedance is. So again, these two are your main filters, your inductor and your capacitor, and then this is your damping circuit. Okay, so now I'm going to go ahead and define the Middlebrook criteria. And basically, if you were to break and the input filter from the converter and then look at the output impedance of the input filter and then do the same thing and look at the input of the converter, you can measure, if you can measure or analyze those circuits, the output impedance of your input filter has to be much less than the impedance looking into your converter. So that's basically the Middlebrook criteria. You want this to be much lower than this. If they're equal, then you're going to have instability. So from the previous simulation, we saw that Z out is approximately 1 ohm. Now we haven't measured this, and typically you would want to calculate. So that's the next thing that we'll do. We'll show how to do that. Okay, so here's an example how to calculate the output impedance of a converter, and I'm using an actual design. My input voltage will be 28 volts, and then these are my 3 output voltages, and of course it has the currents listed here. Excuse me. And once you have those, you can calculate what the output impedance are. Basically, V divided by I will give you your converter's output impedance, but you want to convert that, reference it or reflect it to the input side of the converter. So that's what we do next. So here are the 3.3, the 6, and the 21. When you reflect them back to the input, you get these 3 impedances. Of course, I don't have the efficiency in the equation, but you can include that. I'm just doing this to simplify. Fine. So then, once you have the three, then you basically you put them all in parallel, and you come up with the input impedance of the converter. In the example that I've used, the input impedance of the converter is 92.1 ohms. So if my output impedance of the filter is 1 ohms and my impedance of the converter is 92, you can see that this is satisfied. Okay, the impedance of the filter is much less than the impedance of the converter. So this is very powerful, because now the implication is, if you know what the input impedance of the converter, you can now use a negative resistor to model and do some transient step functions, and you will get some very interesting results. Okay, so here we have the input filter along with the damping circuit, and instead of having the current source, we take the current source and we put a resistor in its place, and we assign it a value of 92. This is actually a nice way to model the converter as well. Okay, and on the right you can see how it's very well behaved. We can see here, this is the step function starts at 10 milliseconds. So it turns on and it goes from 0 to 28, 0 volts to 28 volts. And you see that it goes up and then comes down, and it's very well damped. Okay, so an interesting thing, or a neat thing to do, is to see what happens if you don't have a damping circuit. Now, what I did is I removed the damping resistor, and what I did is, another thing that I did is I went ahead and short across this resistance from the bus. I went ahead and short circuited, and I did that to simplify, and actually to also make the damping more critical. So I can show this oscillation. So if I had left that resistor, it would not oscillate as much as you can see here. Because I left it out, this is seen much more easier, and the oscillation is more pronounced. So anyway, so in this case, you do a transient response, which is basically a step function, and you can see that as you step, it starts oscillating, and it starts oscillating at 39-34 hertz, which is very interesting. So now, once you do that, what you can do is you can go ahead and put back your current source and then measure the output impedance to see what happens, why is it oscillating. And when we do the sweep, in this case we do a AC sweep, and the output impedance actually is 88 ohms. So remember, before Z out with the damper, it was 1 ohms. And now that I removed the R-damp resistor, now it's 88 ohms. Okay. Question is, I don't see no 88 ohms here. I see that the ESR of the 38 is 5 milliohms. The ESR of the capacitor is 5 milliohms. This should basically, if this is removed, it's out. So where is this 88 ohms coming from? Where do we get that? Okay, so that's one of the questions. And of course, this shows that the Middlebrook is not satisfied. So you're going to see that, or at least I've shown that it oscillates, or at least rings. So now, question is, where does the 88 ohms come from? So let's see if we can some transformation. Now, this is all assuming that at resonance, and resonance is at 3934. And what I did is I separated the ESR from the inductor and from the capacitor, and these are actually series resonance. So what we have to do a conversion. We have to go from series to a parallel conversion, and before you do that, you have to do a little bit of calculations. You have to calculate the Q of the inductor and the Q of the cap. Okay, so here is the formula. So basically the numerator is X of L, and this is the series resistance of the inductor, and when you plug it in, you get a Q factor of 188. So then to convert that R ESR, series ESR, we multiply the ESR series times the Q inductance squared. So I end up with a parallel resistance of 176 ohms, which is right there. And then we do the same thing with the capacitor. This is X of L, C, and I end up with the same Q value. And since I'm using the same ESR value, I end up with the same parallel resistance. That's there. So now you can combine these two. It's the RL parallel with the RC with parallel, and that's where you get the 488 ohms impedance. So in case you were wondering where that came from, that's where it comes from. Okay, so now let's see the model that where I saw the negative resistance, and I saw this in the Vache Viporian book, and it's a simple but powerful model. Again, you see everything in here. You got your main filter here, and you have your damping circuit here, and of course your negative. And we saw that this can actually, if you run a transient sweep, you can see whether your bus and your filter node, will it ring or not. So what I did is, this is the switching model. Here is my primary circuit. This is my transformer. Here's one of the secondaries, another secondary, and a third secondary. And the current going through the primary goes through the input filter. So this green is the actual filter, actual input filter. This, the capacitors and the damping are exactly the same as the Vache model. So this is the actual filter, and this is the simplified Vache model. So basically I ran the simulation, and here you can see that if I set the R damp in both, here is the R damp, that is the only thing that I'm changing. And if I plot the current of the filter, or actually the voltage, you can see that they're pretty good. The red is the Vache, and the V filter is the switching model. They're pretty good in agreement. So now I increase our damp to 5 ohms, and again you can see that the Vache model and the switching model are basically pretty good match. Then I did a dirt simulation. I went ahead and removed our damp, and again you can see that you get pretty good results, and that it matches. It shows that you have quite a bit of ringing, and typically the number of ringings that you have tells you the number of Qs that you have. So if you have 5 cycles of let's say 1, 2, 3, 4, 5, then you have a Q of 5. Typically you can do that. So this is a very simple way to check your input filter. You can use the negative resistor model once you calculate the input impedance of your converter, and you can do a very fast analysis and simulation of your input filter. Thank you for your attention. If you have any questions, you can send your emails to my email here, and I will try to answer any questions you may have. Again, if you find this video informative, please subscribe, share, and give a thumbs up. Thank you for watching.